Oh, I'm just going to wait for my headset to connect. If it does. Sorry. All right. Can you hear me still?
Yes.
Okay, great. Okay, thank you for inviting me to give this talk. I will try to motivate and review some of the progress in this direction of merging DFT with supersymmetry somehow. And it's a ongoing work with Chris Blair, who's maybe here in the audience, and Dan Thompson and Alex Sebran. So if I don't know, if please feel free to interrupt me, or if Chris thinks that I said something wrong, I'd be very happy if he corrects me. Let's not make this official or anything, right? But rather as a nice discussion. Okay, so what I have very rough sketch of what I want to talk about. I think there's many things. Oh, this is still ongoing work, and we're still not done. There's missing corners we haven't filled in, but there's still like partial interesting results we have, and I wanna get to that, but I also want to motivate why we care about what we're doing, and what are the open questions, what kind of stuff comes in, what you need to know as preliminaries for understanding this, and maybe I will try to motivate some of these and quickly review. Okay, so there's these two things, right? We have a double field theory and supersymmetry, and they are useful for different things. And so DFT in particular, it's a idea of somehow extending the space-time to accommodate for some of these weird symmetries, like D-duality or maybe later on U-duality, to become manifest, meaning that they become some rotations in this bigger space, this double space, and then there's various problems coming with it. I will talk about it later. There's some constraints you need to impose later on. You always want to kill that extra stuff you've introduced. And so that's the DFT, that's the double field theory, and there's a supersymmetry side of the coin, and in particular I will be talking about superspace in 2D. So superspace has a similar role, but with respect to a different symmetry. If I want to have supersymmetric model, I might just keep that supersymmetry as some internal symmetry, but I can sort of put it at the equal footing with the space-time symmetries, and the way to incorporate it in is to extend again the space, but in slightly different manner by introducing these fermionic coordinates. Probably everyone in this audience knows what I'm talking about, but I will anyway review some of the things as we go on. But so I'll be trying to merge.
But isn't SUSY a space-time symmetry? In some sense, so, it's an extension of the Poincare.
Yes, but what I'm thinking is that, you know, if you have just a model without not formulated in superspace, it kind of, you know, it's like combining the fermions with bosons, right? I'm not, I don't know, it looks more like internal symmetry, right? It mixes those fields. Well, maybe not really, right? But, that's maybe a wrong way to put it. But what I mean is that if you extend into superspace, you end up having something what it looks like, you know, really like some diffeomorphisms generated by some fermionic vector fields, right? Rather than just rotating fermions into bosons, some fields into other fields of different statistics, right? So it makes it more geometric. Maybe that's the better way to put it. Just that superspace makes it more geometric. And likewise with the DFT for T duality, it makes it geometric in a sense. It's incorporating this bigger space into some rotations in the extended space, right? And so particular particular setup I have in mind is that where all these things one can probably study it in higher dimensions and ask similar questions, but the setup I have in mind is two-dimensional sigma model. So I really want to study two-dimensional sigma model. Meaning that I have a two-dimensional source to begin with, so some Riemann surface. Looks like it's squared, so maybe this way. And it maps into some target space, which is our space-time, right? So target space. And what I'll be doing is that I will extend this this side, this world sheet, right, by into superspace, right? So I'll be extending this into superspace or super Riemann surface, and this will be extended into double space. Okay, and so both of these stories are independently understood to some extent. Maybe I will move here to give you some references. So if I have the original sigma model, you know, that's all you all of you know this, right? That's something of this kind. N B N, right? And this thing I can now supersymmetrize and produce one-on-one model out of it. So this is bosonic, right? Bosonic. These are target space metric and B field. Metric B field. And these are the embedding coordinates of that string. Right. So I can easily supersymmetrize this into one-on-one setup. So one-on-one setup. What I mean by that is that I just no longer have these fields to be just functions of some x plus and x minus, or tau and sigma. Right? These are just Light-1 coordinates here, but it could be in other coordinates. But I append some extra coordinates, theta plus and theta minus, right? And then so they become superfields, right? Now, if I you see how these extra fermionic coordinates they would maybe I should ask, do people know stuff about superspace? Does everyone know about superspace or not? Or should I no, someone's nodding their head. No. Okay. So I'll quickly thank you for the feedback. I'm happy to review that. I just don't know the audience. So these are fermionic, and if I do that, I can expand in fermionic coordinates, and why I can expand is because they are fermionic. They square to 0, and so every expansion in these nilpotent coordinates terminates, right? So I can expand. So this would be the first bit in the expansion. Then there will be it's like a Taylor series, right? So there will be first derivative with respect to theta plus, so there will be this guy. Times theta plus, there will be one with x minus, sorry, same thing, sorry. And minus, and then will be one extra bit. X minus. There can't be anything else because theta plus squares to 0, theta minus squares to 0, right? So there's only 4 terms in the expansion, right? Okay, and then this whole field, this super field, it's maybe you should denote it x over an under part, a capital X. This super field is bosonic, and these were fermionic fields. So these guys need to be fermions, worldsheet fermions, and this is again a bosonic field. Right? So these are fermions. Usually people would rather choose to call them psi plus and psi minus. By the way, if someone's not familiar with this notation, x double plus x double minus, that's not equal, but double minus here. It's because of some R symmetry charges of the coordinates as opposed and of these ones. So these are double charged under Lorentz, whereas these are only charged by half charge of these. So that's why I'm choosing all these slight coordinates with double pluses and double minuses, and these ones with plus and minus single use. So that's just notation. You can call them whatever you wanted, x1 and x2, but it's convenient, right? So you see that once you pass to 1-1 superfield, you are you're adding these extra fermions in your one field, one superfield X, right? And now you can wonder how would I how would I supersymmetrize this model, right? What do I have to do to make it supersymmetric? And I mean that's a priori not clear, but there's a you can make a guess, I guess, and that would be that I will, instead of using normal bosonic coordinates I've started with, I will use those super coordinates, and instead of these derivatives, this worldsheet derivatives, del double plus and del minus, I will use super derivatives. So maybe I should say also what the super derivatives are. So before we just had these coordinates x plus and x minus, right? And correspondingly, we had x partial plus and partial minus. And there's also coordinates theta plus and theta minus. So we have these fermionic derivatives, partial plus and partial minus. But somehow they are not transforming nicely. So we substitute these with d plus and d minus, and there are some combinations of these guys upstairs. In particular, I can write this one as this plus this guy. Okay, that's what they are. Now you see the convenience of those double plus notations, because this plus equals 1 plus downstairs, and that's why you have 1 plus downstairs everywhere. It's just, that's just what it is. So these are super derivatives, and now you can write this 1,1 extension of the previous bosonic model. Sigma model. And that would be just what you would probably naively guess. And G n plus B n. Okay, so that would be my Lagrangian for 1,1 model. Now you can also you can expand in the theta the theta coordinate, and then if you read off the theta plus theta minus term, you will get some bosonic Lagrangian, and there will be more fields, and it's guaranteed that it will be supersymmetric. That's why superspace is useful, because if whatever I write using my super fields and super derivatives, it will be just supersymmetric on the nodes. So that's why it's useful. There could be more supersymmetries, and I'll get to that later. And but then it's not as obvious how to pass from bosonic to fermionic. Bosonic to the supersymmetrized version of the original model. But notice that it still depends on the same data. It depends on the metric and in the target space and B field in the target space. There's no extra input which came in, well, maybe except for some spin structure on the world sheet to define those fermions. But otherwise, it's there's no further restriction on the target space. There will be some extra restrictions on the target space when I'll have more supersymmetries on the world sheet. So that's always a mantra in supersymmetric field theories, that if I'm adding more and more supersymmetry, it might render that model more restricted. But if I'm doing in this particular case, if I have just 1,1, there's no further restriction for the target space where I'm embedding my fields. So okay, so that's all I have to say now for 1,1 model. So that's kind of easy. That's what we all know and love. There's on the side of extending the target space into double setup. I want to start with reviewing a little bit of T-duality. So I'm sorry, there's a lot of little bits which will hopefully eventually come together. So T-duality is this weird feature of two-dimensional sigma models we experience in presence of isometry. So what do I have in mind? So if I have this model, I started with here, take it and copy it. So if I have this model, and it happens that it has a isometry, which I mean I can formulate in general terms, but what it really means is that say one of these axes will be such that G and B won't depend on them, right? So G is also a function of X and B is a function of X, right? So let's say X1 will be a isometry direction. So G and B won't depend on X, right? So there will be my isometry. Then I can perform a interesting. Then my model has an extra symmetry. So if this happens, clearly the model will have extra shift symmetry, which wasn't present before, right? If I and the shift symmetry is just that I'm taking my X1 and I'm sending it to X1 plus A, some constant parameter A, right? That was not a symmetry of the previous model for generic G and B, right? It's only present when G and B doesn't depend on X1, because here it only enters in those derivatives. So then I can T-dualize in this direction. And what it means is that I perform this trick people learned a long time ago, and that is that I first make this local. So it's sort of gauging procedure. I add a gauge field such that it accounts for it's still sorry, I'm just going to write X1 here. So I'm going to gauge that one direction, which so this was global originally. Now I'm making it local. And I need to couple to this extra gauge field. Okay. And I'm going to neglect those other terms. Let's just focus on the simplified model where I have just x1 for a moment and say g plus b is just 1, 1. Right? There could be cross terms and auxiliary, those spectator terms. So there, and now I can add a term which will tell me that there's an x hat which acts as a Lagrange multiplier for setting curvature of this two-dimensional connection to be flat. Okay. Right. So clearly, if I is this clear?
So I guess G11 should be downstairs.
G11. Oh yes, of course. I'm sorry. Yeah. Yes. Thank you. Right. So now you see that if I integrated out this x tilde, right, I would find out that this should be 0. Hence, it's pure gauge, and pure gauge, at least locally, means that a plus plus and a minus minus can be written as, you know, some plus plus phi and minus minus of phi, and then I can redefine my x1 and subsume this phi inside x1, and I end up with the same model I've started, right? So you see that if I integrate out that Lagrange multiplier, I will reproduce the original model, right? But if I do something else, if I choose to kill this x1 first by gauge fixing a plus, because now I have full local symmetry, so I can subsume this thing in my a plus plus and a minus minus. So I effectively kill these guys.
That was maybe too fast. What was the first that you?
Okay. Let me get here. So let's maybe make a little diagram. So I had my Lagrangian with x, right? And I've constructed this action L of x, a, and x tilde, right? That's the action where I couple the gauge field and introduce this Lagrange multiplier, right? So this was some gauging. And I can go back down by integrating out x tilde, right? But I can do a different thing. I can transcend to another model, which is in some sense dual to the original model, by first saying that since this model has a gauge symmetry, I cannot integrate out gauge field before gauge fixing the gauge symmetry, right? It's a gauge field. So
the point when you integrate out that is that you say that a becomes d phi, so x gets x plus phi in the model, original model.
So can you repeat that?
So you say that that when you integrate out x tilde, so then you get pure gauge for a.
Yes.
So that means that a is d phi, as you wrote, yes. And then you say that the phi can be combined with the x.
That's right. That's right.
Okay. Good.
And whereas in this direction, I can make such a gauge transformation of a that I kill my x, right? Because every time it enters in the Lagrangian, the a, it comes with this del x, right? In this combination, it's like squared there. So I can say I shift my a by minus del x, right? It's a gauge transformation, right, of the field a. And that way I will effectively kill this del x in my Lagrangian, right? So I'll end up, I'll get into this intermediate level where I used up my gauge degrees of freedom, and I have just A and X tilde. Okay. By using the gauge symmetry degrees of freedom, and then I can integrate out del A. So if I do this, I end up with a, I shouldn't really call it, well, here it's fine, but now I should call it L with superscript D, and that stands for dual. So I'll end up with some model. It's very schematic, and one can generalize this in many directions, but I think I'm already pretty light with everything, and so I'm just trying to give you, flavor of what's happening. So I end up with this model where I have x tilde as my degree of freedom, and that Lagrangian might look totally different. For instance, if it was just modeled with one x to begin with, which is the isometry direction, then that original model would be switched. If I trace through this diagram to a model where I get 1 over g del x tilde squared. Okay, so you see that and that's the typical typical stuff you hear about D-duality if you haven't seen it before, right? But if this would be my target space metric, and this is my dual target space metric. So if it was constant, say I was on a circle in the target space, then in the dual model the length, diameter of that dual circle would be inverted, right? So it's totally different geometry. From huge circle, I got the small circle, but somehow two-dimensional sigma models or string sigma models, they don't see that difference. And it's even better that if these are not constant in those other directions, I end up producing the so I will not only have this term with x1, but I will have those extra terms where there will be x1 bit and the remaining ones. So say this m is this is where I omitted 1, right? So there will be terms like this and b 1m, and there will be terms where there are just spectators. Right, so if I reintroduce back all these fields, and mn plus b mn, I see that when I perform this duality, all these fields somehow mix very nonlinearly, and that's encoded under the name of Busher rules. And what ends up happening is that I produce this new target space metric and B field, but they are still solutions of supergravity equations of motion, even though they are some nonlinear combinations of the original G and B. So that's quite surprising, at least from this standpoint, if you don't implement extra, fancy mathematical descriptions like generalized geometry or double field theory. So that's the duality, right? But now one might wonder. So this wasn't really a symmetry of the model per se, right? It switched the original degrees of freedom for new degrees of freedom, right? It wasn't like a symmetry as what we think of, right? In a sense that there would be two sets of fields maybe, and they transform each other, right? But which might make someone wonder: is there a model where where I would maybe have a double amount of fields to begin with, and then maybe I can kill hard and get one model or the dual model? And yes, there's these models were studied by several authors. I'm not great on references, but particularly there's Duff long time ago. So Duff and what I mostly am going to focus on is Hull's model, Chris Hull. I don't know Duff is definitely before. I don't know if that's even original. Maybe Chris knows, and I'd be happy if he tells us, but it's not really important for now. Yeah, but what this model looks like, yes.
I think Hull started to write something in the mid-90s about this. But I don't know exactly what year the whole model would be from. Is it that some of the first stuff he did?
I'll show you what I mean by the model. I don't know if it's what he first started introducing or not. But what I mean by a whole model is that I can, instead of starting with this x x a m b n g m n plus b m n okay, so it won't be a b. I can start with another model, or I guess I could have just kept the light. I could start with another model which has twice as many fields, and this model looks as follows. It has some age. I will explain what all of these fields are, but bear with me for a moment. I can start with this model instead. And so now, so this would be my model, but it's not the full story. This is the Lagrangian, but there's constraints, so which cannot be implemented at the level of Lagrangian. I need to keep those constraints in the back of my mind, and once I derive the equations of motion, I can implement the constraints. I'll tell you what the constraints are in a minute. But okay, so what are the objects involved? So this thing. So first of all, if I had my target space, this was the target index, right? So that tells me what the dimension of target is. If it was d-dimensional, then this index spans over 2D, right? So it's doubled. So that hence the name doubled model, right? And you can think of this doubled x, this fat x, as something like x, this one, and x tilde. Right. But not quite. Yeah, it's a little more complicated. But okay, so you have this doubled stuff, and then you have this metric on this doubled space, which is called generalized metric. And some of you maybe saw that before. It's a strange object which I don't know if I want to write down, and oh, write it down. People should see generalized metric if they haven't seen it. There's a way to derive this. Not the model itself, but the generalized metric from Hamiltonian analysis of the string model. It's not that I'll just had a vision and wrote this 2D metric. So this is some metric on this doubled space, and you also have the constraints as I mentioned, and the constraints come from the fact that this metric, so it's called generalized metric. It can I can uplift one of the indices by the following. So I can construct new object out of this H. I will call it R. So this had two indices downstairs. So we'll have one index upstairs and one index downstairs. It will be something constructed out of eta m k h k n. Okay, and eta is I will get more to what is the significance of these objects, but it's this matrix for now. Okay, it's 2D by 3D. It's if people know, it's the canonical pairing at my doubled space, but for now it's just some metric which is natural on this doubled space. And if you do this uplift, if you do this raising of one index, you get this endomorphism, right? And you can square it, and you see that it squares to 1, regardless of what the G and B is. It always squares to 1. So every time you get something what squares to 1, you can construct projectors, right? you can take your R and construct this, right? So this is now 2D by 2D identity matrix, and you weight it properly with half, and you get these projectors pi plus minus. Okay, and these projectors they now help you to write these constraints I was mentioning, and they are they're as follows. That's ugly notation, right? Right. So this is these are the constraints I want to implement, and they have two possible, right? They I mean I'm either solving for right. Sorry, these are the constraints, right? So and the way it goes is that if I start with my original model, I derive equations of motion, and then if I implement these constraints, I end up having the original model. But you see that it has all the structures of double field theory somehow implemented in. So it field space has been doubled, and generalized metric occurs in it. And also, so what is now the T-duality is something very simple. It's just some rotation of this space of fields, right? So now the T-duality has become something very geometric. So I can ask myself, what is this global symmetry acting on this space of X and X tilde i's, so on this extended space of fields. And it is some rotational matrix with respect to this metric. So this metric is not Euclidean, it's not Lorentzian, but it's split signature. It's as many pluses as there are minuses. So if you can transform this by similarity transformation into ones and minus ones, and that tells you that the rotations which are allowed on this space are of this form, D, okay, or capital D. Sorry. Okay. So I can perform this rotation, and then if I implement the constraints, I would get the dual model. But it's it's nicely formed at the level of Lagrangian, rather than going through this uplift into parent action and integrating stuff out, and, which is maybe slightly convoluted and maybe not straightforward. Whereas here it's all geometric. Okay, and now you might start wondering if it's possible to do this, if I can marry these two ideas, namely 1,1 superspace on the world sheet, so something that has manifest supersymmetry, and which is also covariant in the covariant double description, which is this manifest T-duality built in. And the answer for 1,1 is yes, and it's very simple. And you would, given all this I've told you, you would probably guess straight away what it is. And what it is just that I do that minimal substitution I did before. I instead of having this model, I kill these partials and I substitute these in them, right? And remove a couple of the pluses and minuses. So what I mean is that I will take my HMN, and here I put this guy, fat M, fat X, right? And the constraints very similarly, they would just be plus minus D plus minus X. So Lagrangian. And constraints. Okay. So cool, that's 1.1. So we can double it, we can supersymmetrize it, and stuff kind of works nicely together. But what I want to get into is 2.2 model and its doubling, and that turns out to be slightly more convoluted. And there was actually original idea we started asking while studying or while starting this project. And yes.
May I ask?
Yes.
So the fat X is now a superfield, right?
Yes, it's a superfield and
so H.
And H
is H superfield, or is it just still the same H?
H is the same field, but now, well, technically it's superfield because now it's so I mean it still depends on these coordinates. So once they become superfield, right? The H itself becomes superfield, but you can expand it in those thetas, right? And you'll see that first of all, I can kill off those. There's no extra information. That's what I'm trying to say. That if I kill off thetas, it still depends on the bosonic part of the superfield, right? And hidden inside double X. So there's no extra stuff coming into calligraphic MN, HMN. And furthermore, even if I kept those thetas, I can expand and I'll see that the whole thing is just constructed from original H and its derivatives, right? Just from chain rule. So there's no extra stuff coming in. It's just that I can take any function and formally make it function of superfields, right? And then expand in those thetas, and it will be just the original function plus the derivatives of the function. Is that clear? Okay. I mean, very naively said. Are there any other questions? Okay, so we have these two things, and now I want to say something. I want to come back to supersymmetry and say something about 2.2 supersymmetry, and that's where the stuff becomes interesting, but also more confusing, and that's where we're kind of stuck in many questions. But okay, so back to 2.2 in no doubling in the target, so just 2.2 superspace. Oh, gee. So the way to go about this is that you start with the model in question, this one. Now nothing's doubled, as I said. And you start asking, when can I add more supersymmetries to this model? So at this point, I use this title, but there's no 2.2 superspace just yet. This is just 1.1 superspace model. 1.1 superspace. And I'm asking under which conditions this model has extra supersymmetry. Okay, so that extra supersymmetry would be, the original supersymmetry was that XM was transforming into some plus minus the plus minus XM, right? And now I'm asking as to whether there's another supersymmetry. So maybe delta 2, and that one would be, I'm going to write an ansatz, J M N. This would be my ansatz, the plus minus X. Okay. So I'm trying to parameterize this new supersymmetry by some field here. I still want it to be, there's some reasoning coming into this. I want bosons to transform into fermions. I want the right dimensions, so it should be dx on the right hand side. I need to match the indices. I guess there, you can do more reasonings about why this form, but no time. So let's take this as ansatz and see what do we expect from these data to satisfy from this endomorphism J. So first of all, I want my supersymmetry needs to square to translation, and also I kind of want these two to commute with each other. So if I require that, I'll find out interesting, very fascinating thing which has been noticed a long time ago and developed and generalized in many directions. I'll learn that this object, this a priori, free endomorphism on my target space fields, it's actually complex structure. And by complex structure, I really mean complex structure, meaning that it squares to -1. That makes it almost complex. So it's complex. And so meaning that it squares to -1, and also the Nienhuis tensor is 0, right? So so that there's some integrability condition for J, and that all comes from closeness of this extended supersymmetry algebra. Okay, so that's very nice. So Nienhuis. Okay. So yeah, so that's what it is, and right. But you can then, one particular generalization is that no one told you to begin with that this right. So there's this nice feature in 2D that those right-handed supersymmetries and left-handed supersymmetries, they are sort of independent. So I could instead of having one J, I could have two of them. Okay, can happen. And it turns out that if I run the same reasoning, I find that both of those J's, they need to square to -1. They satisfy some integrability relations, but they define different type of geometry. So what happened? So if okay, now I'm going to make a table. So if J plus is equal to J minus, it turns out that all these constraints I need, it will turn out that J, so it's just J. J will be complex structure. And furthermore, J and G together, they will form Kahler geometry. Geometry data. If I have this more general setup, where J plus is not equal to J minus, I still have some interesting geometries, but they are called now generalized Kahler geometries. And this is where fun begins, and where a lot of complications also arise. So this yields something called generalized Kahler. Kahler geometry data, and basically it's a pair of J plus, J minus, and G, right? And you can and there's several different flavors of this generalized Kahler geometry which show up, and the models behave very, very differently for each case. The mildest type of generalized Kahler geometry, there's like a spectrum of these. I would say that you can on one side, what comes in out of the analysis is that if J plus communes with J minus, now there are two different complex structures, right? So I can study whether they commute or not. So if this happens, the geometry is called BILP, by Hermitian local product geometry. If they sort of what do you say? if they anti-commute, they form something you might be familiar with from before, and that's hyperpolar geometry. And then in the middle, they can commute, anti-commute to some extent. Some bits, some parts of the J plus might commute with J minus. Some might not, and that's generalized Kahler. Okay, and so these built ones, they are the simplest, and the reason for that is that if I eventually want to pass to 2,2 description, and 2,2 description it makes my superfields even bigger. So instead of repackaging my x into x plus plus, x minus minus, theta plus, theta minus, I add extra pair of theta plus and theta minuses. Okay, so these will be 1 and these 2. Okay, and then I want to combine these into some complex combinations. So also I will have more of my d1 and d2 super derivatives, d1 and d2. And now I want to construct these combinations d1 plus minus I d2 somehow. That's what you're taught when you're studying 2,2 superspace. But what's usually hidden under the rug is that this would be my d and d bar, right? What's usually not really stressed out is that it's already done when I've diagonalized my target space complex structures. So I really, I can a priori write something like D acting on XM to be D1 XM plus J minus M N D2 XN. And there would be another one for BART. Copy paste. For BART guy, okay. But now the thing is that if it turns out that the recalling linear algebra statements about matrices, if these two commute, I can mutually diagonalize them, right? And then I can subsume these J's and J plus and J minus into redefinitions or change of coordinates of axis into some holomorphic and anti-holomorphic coordinates, right? And based on so if I can get rid of these J's and in different coordinates, and I end up producing these phi. Maybe I want to this. Okay. Paste. And these will be just I's. Okay. Right. So that's why I create these holomorphic and anti-holomorphic combinations. But this is really only when J is equal to J plus is equal to J minus. If it turns out, so why is that? Because then I really I really have my J, and I in the diagonalized basis I know it's it squares to -1, right? So there will be same number of I's, the same number of minus I's, and that's why I produce out of these combinations D's and D bars, right? Acting on the phi's and phi bars. Okay. But if I have J plus and J minus, which still commute, so build case, but I they are not the same. Different things can happen, and what basically I can separate stuff. This looks like it's equal, so maybe this way. I can separate my J plus and J minus into two blocks. So there will be zeros here and zeros here. And what do I want to say? So here I will have part which is same in left and right part. Right. So there will be some amount of i's, some same amount of minus i's here, i's, minus i's. But then there will be block where there will be some i's and minus i's. Again, same number of them. But here it will appear with the opposite sign. Okay. So that's the only thing which can happen. There will be two blocks in one block they agree in left and right sector. In the other block they differ by a sign. And this is a reason why I need different types of fields introduced when I'm passing to 2,2 description. So yeah, I haven't. Wow, it's 2. Okay, how much time do I have?
Yeah, you can take as much as you want, so we still should have some time to prepare for the string journal club, but you can take some time.
How about I talk for half an hour, and I don't know, I could also I mean, I can like super rush or something, or I can just say these things calmly, and then maybe depends on how many people you have for the rest of the semester. Like I can maybe speak one more time if people want.
Yeah, you can speak one more time, but we are full by the end of the year, so at the next semester you can speak to your second half if you want.
So maybe I'll just try to introduce everything I want and say what we're trying to do, and then I can provide more details.
Yeah, sounds good.
Okay. Next time. Okay. So right. So that's what happens here, and basically, so if I have just this block where stuff agrees, I'm led to when passing from 1,1 to 2,2, I can use these fields called chiral fields. I need to I didn't say that yet, but it's clear that if I have more of these thetas in my expansion of the field, there's way more degrees of freedom to begin with, right? So I need to cut it down somehow, and I need to cut it down in covariant manner. And the way to do it is by imposing these constraints. These are different constraints. They have nothing to do with those double constraints. We have no doubling here. Right? So I have this, and if I have constraints like that, so both plus minus, I call these fields chiral fields. And I need as many chiral fields as there are as is half of the dimension of this block where left and right complex structure agree. Okay. If they agree up to a sign, I need different type of constraint, and this constraint is called twisted chiral, and it does the following. It's something. Well, it's twisted. I'm gonna write as chi, as it's usually written. And chi d. Okay, so these are twisted chiral fields. Cool. Okay. So if I'm so in other words, if I'm so then build geometry, I can pass to 2,2 no problem, and I need these chiral and twisted chiral fields. Okay, and now the problem, and yeah, there's I should maybe say what there's a nice thing which happens in all the build situations, and that is that I can rewrite. So maybe you know that I will tell you for the case where G plus is equal to J minus. You know that that just from the fact that J and G form a Kahler data, right? You find out that G is actually a very special form, right? It's not just any old metric, any old symmetric metric, but it's actually Hessian, if you will, of some function, right? And that function is called Kahler potential. So there is this function Kahler potential. Well, it's not a function, but it can be. There's some gauge transformation it has, but potential. So in Kahler case, I only have phi and phi bar. This Kahler and complex conjugate of chiral fields. So it's a function of these two. And if you are wondering what this metric is in terms of this function, you just take the derivatives of the v, and that would be your metric. That would be the omega, right? And from from multiplying by j, you get the metric, right? So somehow Kahler geometry is repackaged in this very efficient data, which is one function, Kahler potential, which is not a potential. It's not a function. What I mean by that is that clearly this is the only geometric data I have, and if I shift this v by something that depends only on phi or only on phi bar, it doesn't change, right? So there's this ambiguity in v. That's why it's not a function. It can be changed by shifts by something fully holomorphic or fully anti-holomorphic, right? Okay, cool. So that's that. And in build, there's a similar thing happening. In build, you get a function which is called generalized Kahler potential, and it will depend on phi and phi bar, and chi bar now. And similar stuff will happen that I can reconstruct G out of this function by taking some derivatives, and stuff really works nicely because I was able to find these phi and phi bars. Cool. Okay. But stuff goes wrong if you start wondering what happens in the general case if J plus doesn't commute with J minus. And the reason for that is that you no longer have these nice coordinates. You cannot diagonalize J plus and J minus. You cannot really define these nice constraints on the whole set of fields, which would describe the dynamics of this type of target space. And you're led to need to introduce these semi-chiral fields, and they are fields which have weirder constraints. They are not of this nice form, and now you can in principle have some potential, but it will render that model very nonlinear in terms of this original function v. So the G and so these omegas, they will be some ugly functions of the v, and stuff just doesn't look very nice. And that's so all these complications come out of the complication when J plus and J minus do not commute. But there's this thing which originally motivated why some sort of doubling might help. So I wanna say something about that. Why doubling might help us out. So I want to, sorry for scrolling. I want to just take this one equation and okay. So I don't know how many people are aware of generalized geometry. I think many of you who are coming to the journal club are probably, but the thing is that maybe I don't really have to say much about it. But imagine that if you somehow doubled your space of fields, you wrote this strange combination of i's and omega plus omega minus. What I mean by omega plus omega minus is that I just construct this these two forms out of my g and I plus minus, which was j. Sorry, these are all the same. So I. Sorry, class. Can you hear? Can other people hear me, or is it just Klaus who has trouble?
It's fine for me.
Yeah. Okay. Right. So I can construct this huge object, this doubled object again, and somehow this object is very beautiful because it plays a role of some analog of complex structure on some doubled space. And what I mean by that is that it again squares to -1 as the complex structure do. But what's pretty is that regardless of what I plus and I minus are, this doubled plus j plus and double j minus, they commute always. Okay, so you might starting, oh, okay, maybe if I double my space of fields appropriately in this 2,2 setup, and I switch from the original I plus and I minus on the the original physical space into this doubled space where I'm using these guys, I fed j plus and fed j minus, they always commute. So I can maybe maybe I can mend this problem with having ugly fields corresponding to non-commuting parts of my complex structure, and I can rewrite the problem in a nicer way. So we haven't been able to do that, but I think we're on the, hopefully, optimistically speaking, we're on the right track in that direction. But we know a couple other things we can do. So I'll get to what we can do, and I will speculate on what we can do just yet. But maybe I'll pause for questions if there are any. So this object somehow also plays nicely with another evidence for this being somewhat relevant, is that in Hull's model, we had this HMN, and that thing also interacts with this JMN and J plus and minus MN. Okay, so these structures they somehow play nicely together. So there's an evidence that if you use these complex structures and this generalized metric in the appropriately extended field space, things will become nice. And what are these properties these three fields share? So they sort of work as the usual Kahler data, if you will. So in normal Kahler geometry, right, you have this omega, I, and G, and you know that J, I is omega, right? here you have two complex structures, and that's a nice thing about generalized geometry, that it somehow blurs this difference between I and omega. So you can think of one as I and omega, the second one as omega, or more like some combination of these, because you see that the J plus minus, it depends on both I and omega, right? So somehow it has both data at the same time. And there's a similar relation. I could also do this instead, so I can express the metric in terms of omega and I. And indeed, I can do the same thing here. I can write my, not H, but this R I defined before, but that's just the one with raised index. So pretty much the same thing. I can write it as a product of J plus and J minus. And this has been studied in generalized geometry literature. They exactly under the name generalized scalar geometries for obvious reasons, because it's generalized geometry and it resembles this scalar geometry setup. Also for very special case where I plus equals I minus, you'll see that this will actually give you so if I plus is equal to I minus, you can observe that it will just be this for I plus. And it will be for I minus, it will like this. Okay, so it will repackage the original I and omega in this bigger thing and put it sort of on equal footing, and sort of make it look same as the other extensions of the color geometry, geometries. Okay, so now,
sorry,
yes.
can I ask? So
yes.
I don't really see how you can get R from this these double J's, because this R, that's basically just a generalized metric, but with one index raised, right?
Yes, yes.
So it contains both the metric and the B field, but
That's
I don't
right.
really see where you have the B field in your definitions of omegas and I's. Like they are related together with the metric, right? You can get the metric because the omega and I are related with the metric together, but how you would get the B field?
I mean, it. Wait, I don't understand. So I mean, it really comes out of if you. So you agree that if I have this scalar case, I get the proper G, right?
If you have this concrete splitting, you mean?
Yes, yeah, right. Because I multiply these together, and I produce. So if I multiply these two together, right?
Yeah.
I produce something like this. No. I produce G inverse and G, right?
Yes.
There will be no B field, right? But there's no B field in Kahler geometry, right? But there will be. It will just come out of what I call like. How should I say? I will, right. So there will be some combinations of I's and omegas, which will have antisymmetric part, and they will produce the B and G parts. So it's just that.
So you will have to identify some combinations of I and omega and call it your B field. Okay. And that makes sense. Yeah, thanks.
Yeah, it's not clear from here, and also if you know the generalized geometry data, the way B field sort of comes in is from it comes somehow implicitly, right? You know that the omega plus omega minus are no longer closed, but their difference is the d of the B field, right? So it doesn't really come somehow explicitly, but it appears. So that's the case. Okay, and okay, so what? So now the question is, can we do the similar thing as before? So now we want two things. We want I showed you how one can how one can construct this 2,2 and what are its limitations. So 2,2 on world sheet. And doubling in the target. Okay. So we want to do both things at once, and we can sort of do it, but what we can do is that we don't seem to be finding the right fields. So we start with, as I told you. So first of all, we can do it in build case. So I will I'll fix to be in build case. Then I can have my fields chi and phi bar and sorry, phi and phi bar and chi and phi bar. I construct my model, which is just given by some function p of phi and phi bar and chi and chi bar, and I can now extend this space of fields to have more fields. So basically, I double the space again. So I will have chi. Sorry, I will have chi tilde bar, phi, and tilde. Why did I switch the order? It's that the rule of thumb is that I for each set of phi and phi bar fields, I need to find a pair of twisted fields, and for twisted pair at the beginning, I need to find a pair of chiral fields. So if I do this, I can bunch them together, and I can write this bigger Kahler potential or generalized Kahler potential in doubled setup. Generalized. And it will so there's some stuff behind I cannot really explain in 8 minutes, but it will be the original potential, and there will be some extra stuff, some extra potential, and extra the tilde, which will be a function of these tilde coordinates. And but don't forget, so this should be an analog of doubled so Hull-like model in 2,2 superspace. So I want it to be defined on these doubled 2,2 superfields. But there was a the set of constraints, right? And by those constraints, I don't mean the ones coming from superspace. Those are extra constraints because of the 2,2 superspace description. But there are the Hull constraints, right? The ones from the very beginning, plus, minus, right? These ones. So these now also uplift to 2,2 description, and they're very strange. They somehow modulo some complications. They are basically connected to the original fields in this way. And I'm sorry, yeah, this is not exactly right, but I'll maybe fix it next time. It's basically that I have those dual fields connected to the original fields via that original potential. So I have my V, and I define these dual chi's as like Legendre duals of the original fields, and also this V, it will it's Legendre transform of the V itself. So now I have this model where I have V and V tilde summed together. So in particular, this doubled V, it's Legendre self-dual that we call it, meaning that if you do the Legendre transformation, you just switch these two bits of it, right? And so it stays the same field, same function. And these constraints are also constructed from the original. So this is the original. Sorry, it's not the double. Right. Yeah. So you have now this model where it depends on I and phi star and phi and chi bar and phi tilde, phi tilde bar, phi tilde, phi tilde bar. And it's Legendre self-dual, and there's these constraints. However, so that's something we can do in under some special circumstances. I will not go into detail here. You can show that if you solve these constraints and plug them back in, you end up having the original model. If you solve stuff the other way around, you can also say, okay, I'm going to, right? So these are equations for chi tilde in terms of V's, but I can also say I would solve say chi's in terms of phi tildes, right? Yes, using the other bit of the potential. So I can choose the other direction where in which I'm going to solve, and that way I would basically drop out this V and keep this V tilde, and that would be describing the dual model to the original model. So in that sense, this model is playing a role of the parent action in 2,2 description. We have some double potential, and you either solve constraints in one way and produce the original model, or you solve it in the other way and produce the dual model. Right. What's not great though, and that's something we're constantly puzzled about, is that these if you start asking yourself a question. So yeah, another thing is that we can reduce also the from 2,2 to 1,1. I didn't say what that is, but basically there's a procedure where you can integrate out half of those superspace directions and produce 1,1 model, and we can produce that whole model. So that's something what can be done. But the thing is that in terms of these coordinates, now you can ask, what are those complex structures which are used to extend that supersymmetry of the original Hull model? So you could have also started from the direction. You could have taken Hull model and start asking the same question I asked for normal model, as in what extra structures I need to extend it to be, to have extra supersymmetries. But there you find out from calculations that it's not these pretty J plus J minus fat, J plus fat, J minus, which make this model having extended supersymmetry. And so we're sort of hoping to find some better set of fields in which these will be exactly the right complex structures used to extend the supersymmetry. Why is that needed? Because it seems like upon extending in this way, by choosing these fields, which are Legendre dual to the original fields, you're not really forming some covariant ODD multiplet. So it's not really there yet. It appears like, so it seems like Hull model, but it's the wrong set of fields. And if you were to ODD rotate them, they would not transform covariantly, and you would not really get the right by transformation properties. So it seems like we need to find different coordinates to put it in together and manifest these generalized complex structures in the model. So okay, so maybe that's I have like 1 minute to finish. So I'm just maybe I will recap what I said. Right? So I was talking about I'm sorry, yeah, I didn't probably get to like main point, but at least I feel like I've introduced what was the driving force for the project. So maybe that's more important. So we saw how how we can have the 1,1. Actually, I will make this picture maybe to finish. So we have the original model. And that can be doubled to Hull model. Original model can be easily extended to 1,1 and associate model, superspace, maybe superspace. And that can be uplifted to 1,1 Hull. But the question really is, do we have the right coordinates here? And what even happens if we go further to 2,2 superspace? Is there a proper 2,2 generalized doubled potential? Description. And so that somehow what we're trying to do to get to this model, we seem to have it, but in wrong coordinates somehow. And the open questions really are like, where are these? So how do we see J plus minus? Because if we have them, we can rotate them nicely. They transform nicely under ODD transformations, and they therefore what's the full hope is that you will have this doubled model where you have axis and x tildes, and by different projections you produce two models. So you model with x and model with x tilde only. But if you want to do T-duality, you can just rotate stuff up here and project down to the physical model and produce dual description. What's even better, and what was the original hope for using this description, which is still elusive, is that we could start with something with build geometry here, and which is the one with commuting complex structures. And upon rotating under ODD, we can actually make those complex structures, which should be downstairs in the physical space, non-commuting. So you can even accommodate for the geometries which have no description in terms of chiral and twisted chiral fields up there in the doubled space where you've doubled the number of fields. So that's the original hope, and that's something where we're headed, what we're trying to achieve. So maybe I'll stop here so that I keep you listening to me for 2 hours. But okay, so I'll stop here, and if there's any question, I'll be happy to answer that, or maybe talk about it some other time.
Yeah, okay, thank you very much. It was a nice talk. I just wanted to ask, can you show the picture you have just above here? Mm-hmm. Yeah, to me it seems like you have more ways how to get to that 2,2 generalized double space, right? You can, as you said, you go from the 2x2 2,2 superspace and you double it, but you could also be in your 1,1 doubled Hull space and try to add some supersymmetry, and in theory you could end up in the same space. So is it equivalent, these two approaches, or is it just doing the same thing?
That's a good question. It seems like, yeah, okay, I'll answer a different question and first. Sorry, but to go into 1,1 in physical space, you first need to go to 1,1 superspace and implement the Hull constraints, or first implement the constraints at the 2,2 level and then reduce to 1,1, right? So you can just reverse the arrows. That's what I just described. And this somehow doesn't seem to be equivalent. It's only equivalent in very special circumstances, under very special circumstances. So that's also something what doesn't seem to be fully working, like the ways of reducing and imposing two different constraints at the same time. Like it seems like there's only one preferable way to obtain the physical model, and that's puzzling. And that's maybe because we are really using those wrong fields. But yeah, that's something we don't yet know. So I'm not sure about the other direction either. Usually we just wrote some ansatz and just check it whether it yields the same original model on implementing these constraints. But it's true that these two directions often don't yield the same result. So there's still some not very well understood stuff behind the reduction.
I see. And you mean they don't like give you the same model, or they give you the same model but in very different way that you can't really say if it's the same?
No, they just don't give you the same model. They just But also those Hull constraints, they are slightly different. You can't really implement them at the level of Lagrangian, right? They are like self-duality constraints in the angles, right? If you have self-duality angles, you cannot really write down Lagrangian. Neither can you like solve for those constraints and plug them into Lagrangian to just yield topological theory. So it's similar with Hull. You need to just keep them in the back of your mind and then impose them at the level of equations function. So maybe that's the thing. Like there's another way of implementing the constraints in the whole model by gauging some symmetries, and maybe that's the better way. And so you gauge some symmetries and then integrate out the gauge fields, which is maybe a little bit aligned with the picture with the parent action. Maybe that's the more kosher way to approach this. That might make this square commute, but at this point in time, I'm not sure.
Okay. Yeah, thanks. Yeah, so do we have any other questions?
Yeah, can I ask about your last point? I didn't quite follow how you go from J plus and J minus commuting to them not commuting by an ODD transformation.
So, okay, maybe that I can still write. So if you write this fat J plus J minus, right? I just constructed out of I plus I minus, right? So say I start with the ones which are commuting, and I construct this huge I plus I minus. And if I rotate it by ODD from both sides, so it's endomorphism and transform covariantly. So I would have some R inverse J plus minus R. Now I can read off the this block, right, again, and read what are those I plus I minus complex structures, right? Which are the ones on the Heft space. It turns out that under certain type of ODD transformations, those new complex, right? So I'm just reading it off the double J's. So
but the J's would still, if the big J's were commuting, they're still commuting after this transformation.
Of course, these will still commute. So what I mean is, sorry, I'm saying it in a poor way. I have these transformed. They are still commuting. They always commute. But the way I extract I plus I minus, which were the ones defining the original 2,2 fields, if they commute it in one frame after rotation, they the ones I extract from this J tilde, they might not commute.
Okay, yeah.
So that the hope is that once we're done with this construction, if it's possible, or if we're smart enough, then it doesn't matter whether you have the semi-chiral description, because if you double, you will anyway use these double J plus minus, and they always commute. You will have always some sort of double chiral and twisted chiral fields.
Okay. Thanks.
Any more questions? Okay. If not, then thank you, Ondřej, very much for the nice talk, and we'll be happy to have you again, maybe next year, or we can also do this year, maybe some other day. But as of now, I think we have full schedule up until the end of the year. Or if you want to go at Christmas, then I don't know how many people would be here to listen.
No. Yeah, I mean, I'll be happy to talk more, but maybe after the New Year we'll have more to say about the. Yeah, now I'm getting to the disappointing part if I talked for longer. So I guess it worked in my benefit. That now I'm getting to more confusions than the answers. So maybe we'll know more in a couple months.
Yeah, well, I hope that you will solve everything by then, and you will tell us how it works. Yeah, okay, so thank you very much again, and thank you to all the listeners, and we'll see you next week, and we'll have Radek Kitsia talking about inverse problem of calculus operations, and then I will send you an email with the abstract and title. Okay.
Bye.
So see you, everyone.